Listen on.
Welcome everyone to the final TomTom IKD session. Today we will talk about the Kiln shell laser. My name is Tom Zhang, Senior Engineer for Industrial Kiln and Dryer, and I have here today with me Thomas Stutz. As you guys have seen this, these types of webinars now, first thing I would like to say is please make sure your webcams, you can see our webcams, because we will be showing demonstrations of where Thomas will show some of the instrumentation, some of our guys in the shops, things like that. If you guys have any technical issues with the GoToWebinar or anything related to that, we do have a crew on the backside that will work with you to help you guys out, so feel free to ask some questions related to that. So again, today's final session, me, Thomas, we'll go ahead and start chatting. I think we've gone through this multiple times. TomTom tools, great instrumentation, many different countries. And one of the things we want to do today is go through the Kiln shell laser. And with the Kiln shell laser, there's various components. And Thomas, if you want to go over the components, I'll switch it over to you.
Yes, okay. Okay, I can show it. So
okay.
Here, that's the box. So here it comes. We have the laser. It's a distance sensor, which measures the distance to the kiln shell, and with that we can measure the roundness, and we will show later. Then this is an electronic unit, so it needs to be protected from the heat radiation from the kiln. So we have the heat shield, it's held with the magnet. And then we need a tripod. A tripod, we use one from the photo equipment or photo cameras. You can use any, right. It's a standard thread, or we can have for a quick measurement, if you just want to measure one position where you have access to maybe somewhere to a structure or a beam or something, you just can clamp it with the G-clamp. So,
yeah, I've used that on the handrails.
Yeah, on the handrails it works as well, but still be careful that it doesn't drop, especially when we have right. Maybe vibration around the kiln drive sometimes. Then it's so here we have different threads. We have this photo thread with that's the 1/4 inch, or we have M6, but the stand here is 1/4. So then we can clamp it, and that's it. Here of course we need a charger. It's rechargeable batteries inside, and then we have another tool which it's a helping tool. It's not really essential to measure. We can do it just by that. But later I will show you when we talk about the measurement. We have to indicate the rotation of the kiln or the dryer, that we know where is the let's say the 0 point or the starting point of the geometry we record. And to help, we can use this. It's called rotation trigger. So it triggers the starting point. This is it's placed on the girth gear usually, because there it's not too hot, and then we can let it run around the kiln, and while it's turning, it's always sending the rotation position of the kiln, and this helps to measure.
Does the distance measure, or does the distance matter much on the rotation trigger? Let's say you got a 600-foot kiln.
Yeah, it depends a bit on the disturbance around. So if we have a shield, you know, when it's running under a cover of the girth gear, maybe then the range is limited. But if we have a free side to the gear, then it can go very far. But it's
Wow.
it's always a little bit the surrounding as well. So if we have troubles with radio frequencies, it's a Bluetooth. It's with Bluetooth but with long range. And if there are no obstacles, it goes very far. But as it turns behind the kiln, so then we have the kiln between us, then we might have a little bit problems to reach if we have a very long kiln. But for the most of the kilns, especially with the 3 piers, it should work. Maybe you have to place it when you go downwards, you place it downwards. That's the best. Because upwards there is not much distance to the inlet. It should be easy to reach. But downwards, from the gear down, it's a long distance, and that's why you should place it on the downward side.
And that's assuming you have the long-range Bluetooth adapter on the unit, right?
Yes, exactly. For all our tools, we supply always this USB long-range Bluetooth adapter, which makes it possible that we really reach very far. We don't need it for the laser itself because we are very close to it, to the tool, so it's not the problem. But we have seen, or we discussed, the quality sensor, and the quality sensor is going behind the kiln. So when it goes behind, then we have the kiln between, and then we need a strong Bluetooth, and that's why we are using that. The better option, instead of sticking that into a laptop and then we have it exposed, we can hit it and might damage the USB port on the PC. So that's why we are recommending this kind of tablet PCs, which we are using in the field. So it's really robust. It's a Panasonic. And here we have made this Bluetooth adapter. And this is the same as we have here. It's the same electronics, but it's integrated in that housing. And with that, we have a good Bluetooth to work with all our tools.
And one comment on that is that antenna that sticks out, you can unscrew that.
Yes, exactly. For transportation, we remove it. So, and then it's hanging here. It's secure. But even if you would break it, you can put any other antenna, Bluetooth antenna with a SMA connector, which you can find in the internet. You can find. It's a standard. It's a 2.4 gigahertz antenna, and you found any kind of. You can have longer or shorter, and yeah, if you are in need. Yeah.
And on the toughpad, the Panasonic, you could use that for any of the other TomTom tools. Also, it's a separate package.
Yes, exactly. If you break one of these or you lose it, you can take it from the other one and you can get a new one in the meantime. So it's they are interchangeable. It's the same. Right. It's Bluetooth standard with 2.4 gigahertz frequency.
Right.
The same is for the charger. The charger, for all our tools, the chargers are the same. The chargers have the different country adapters. When you have different plugs, you have all them. You easily replace them. That it fits to any, and the voltage range is from 100 to 240 volt. Yes.
Cool.
Okay.
All right. Awesome. So what we're going to do next is we'll talk about some of the measurement principles. I think, Thomas, you talked a little bit about it on that. It is an optical sensor, and what it does is it emits either a laser or some kind of light that reflects, or the light reflects off the shell to where you can get a distance. The goal is to get a distance from the laser to the shell. Once you get that distance, the variation in the distance is what will give you the curvature on the units. Mm-hmm. So then as you go through, as you go through axially going uphill, downhill, and then the variants, we create ultimately a topographical view of the kiln shell that you can either make into something like this or a topographical view that's flat. So that's the overall principle. Any comments you want to make on that?
Yes, as you said, I mean, all what we want to measure is the change or the variation in distance. The distance, the absolute distance, you know, from here to the kiln, if we are, let's say, 4 feet or 10 feet away, it doesn't matter. What matters is that this is more or less stable, does not move during the measurement. Small vibration, they do not harm, but not moving around or don't move between. So it just measures to the kiln shell. And if you measure from below, you can stand on the ground, or usually we go to the side on these catwalks from the piers. So then we are closer or further away. It does not matter, only the variation. But what we also have to say, I mean, the kiln has to turn. A stopped kiln we cannot measure, it's not possible. It has to rotate, right. and preferably in full speed. I mean full speed, in normal operating speed, because then the measurement takes less time. If we would think about measuring the kiln in the auxiliary drive, when we have 10 minutes per turn, then it would be a very long measurement campaign, and we would collect too many points. So the system is made for normal rotation speed, which is typically maybe 2 RPMs up to 5. And then we measure one turn is enough. If we think it's not enough, or we missed maybe the reference point, then we do another turn. But when we are when we are used to do this measurement, we can do it in one turn. So one turn measuring, one turn of the kiln is relocating the sensor, and then we do a next turn. You know, then we have in a few kiln turns we have done a lot of the kiln is covered.
Right. Yeah, because it's when you do a half RPM kiln, and that is the full speed, and it's, let's say, 200 feet, it takes a very long time. So it takes a very long time. Yes. Yeah. So yeah, but usually, yeah. No, I'm just saying that's just the logistics of it. Yes. No, newer kilns. I mean, at least in the cement world, they are running faster and faster. So we are running. There are kilns, they are running more than 5 RPMs. And that was also the reason why we have made that. In the beginning, we measured with traditional laser sensors, which you can buy standard ones, also with Bluetooth interface. But the problem was that they only collect maybe 2 points per second. And when we have 4 RPM, so we have only 15 seconds for one turn, and with these 15 seconds we get only 30 points, then the resolution is not good enough. Then we would need to wait more than one turn. We would have to make maybe 5 turns or something like that, and then it's too much time consuming. So that's why we developed that. We found a laser sensor, which a module inside, which can shoot 10 hertz, and that's why we are measuring with 10 points per second. And with that, usually we get with one turn, we get enough points to have the profile. Okay, cool. So we talked a little bit about the measurement principles, and we can chat a little bit, Thomas, on the measurement setup. And as we talk about it, I'll start kind of setting up the guys over at the shop. If you want to talk about, you want to get it close to the center and any of the readings, please. Yes, here this sketch on the right side, it shows exactly how is the setup. So we have the tripod and we have the laser, and it's directed or aimed to the center. I mean, more or less. So
It should not be too far out of the center, because then we would the readings would not be as accurate. So the better to the center, the better the readings, but it's not so sensitive. So just by looking to it, it's good enough. Then you
right.
Then we measure this distance, recorded distances there, written. Yes.
Right. Cool. Well, okay. Well, it looks like the guys are starting to get going. I'm going to turn mine off. I'm turn yours off. I'm going to show the screen. Okay. So what we have here is the test unit that we have. So on the screen with the unit, the Kiln shell laser is pointed at the unit. If you guys can show the laser itself, I think I see the laser there. It's roughly about center, what Thomas was saying. That's one of our Kiln shells, and there's the laser itself. So once you guys have the safety done, please go ahead and rotate the unit, please. Okay, cool. So once the unit has started rotation, we're going to start taking some initial data. And the cameras, this is the interface on it. It's much quicker with the camera in this way. If you guys go ahead and start taking the measure, go ahead and click play, and you should see the initial movements. And it gets, right now, this is a relatively okay unit, but you see how it's getting bigger and bigger. So the run out on this unit is getting bigger and bigger, and now it gets smaller and smaller. So this happens every revolution. Like Thomas said, 1 is good enough, or 2 if you're not comfortable with what's shown up, or if it's too fast. If it's slow, for sure 1, because it takes forever to do that. Why don't you guys go ahead and stop the measurement. You can keep the unit running. Go and stop the measurement and show kind of the topographical view a little bit. So this would be, each step as you move across the unit, something that this would look like. So looks like towards the beginning, there's a little bit of a high divot towards the end. And the thing is, sometimes you can definitely see it, but a lot of times it's hard to see, especially with the distance you're at. Luckily with this unit, we can just go up to it and take a look, but not all the units you could do that. So this is where the power of this measurement comes in. So I appreciate it, guys. We're going to go back to our screen. Thank you. Okay, cool. So that was neat. I think, here you go, Thomas. Mm-hmm. So that was the setup. That was the measurement set. What we saw was, let's see here. What we saw was the unit itself moving. What we saw was the setup. It was close to the center, and eventually we would move it, like in this image right here. Let me make sure the audience can see these images. Okay. What we could see on the images here is that you move it axially along the unit to ultimately create a full kiln profile. Mm-hmm. So here's the different views that we can see in the software. You got a grid view. You have an amplitude view. This tells you your highs and lows, and then this curvature view. And Thomas, this is going from one axial location to another axial location with some of the divots, right?
Yes, I can show later a little bit when I can share the screen later, and then I can explain.
Cool.
Yes.
Yeah, absolutely. I think I got one more slide here.
Yes.
That talks a little bit. Let's go through the limits a little bit, and then for sure let's share your screen and discuss more in detail on some of the results.
Yeah, maybe something to add to the measurements. Typically, we measure every meter, but you can also make a finer grit, but usually on this big equipment it's not really needed. But it's just maybe for when you see by eyes, you see that there is a deformation or something, a bump in the shell. And when you go to stiff to full meter, that this bump will be exactly between, then of course you record one more, or you don't go to full meter. You can also make in 25.5 meter or 25.3 meter. You could record. It would not disturb the 3D model. So you place wherever you have access, or sometimes when you are close to the tire, you have maybe some blocks or whatever fixation of the tire, which will create disturbance, so you can shift it a little bit further away.
Right. Typically, that's either the pier, the conduit, or like the heat shield. Those are typically in the way.
Yes. So you go a little bit further away wherever you have access. But sometimes you even if you have a small gap between the fans or heat shields or whatever, you can shoot through with the laser, and as long as you hit the kiln shell more or less perpendicular, it's already fine. What I would recommend is, when you think about taking these measurements, and also if people in the plant, they are asking you or somebody else to measure that, then it would be good if you make the meter counting on the kiln somewhere fixed, like on the handrails, that somebody goes there and scribe what position it is. That everybody who is doing measurements on the same kiln, that everybody talks about the same position, that we don't mix up the metering or whatever you have. And I would recommend to use the 0 point, the starting point at the kiln outlet. Because when we talk to refractory people, they always start counting from the outlet, because that's also the place where we start to install refractory. So metering of the kiln should start at the outlet, and then 1, 2, 3, 4 up to the inlet. And
and I know some of the customers or even some of the plants we go to, they'll mark that location every meter to where we can kind of go in and see it. So that's very helpful. Then we're all on the same page.
Yes, and it also corresponds to the picture in the shell scanner, because usually they have a temperature scanner installed, a fixed installation, that we can see the temperature of the kiln shell in the control room. And there is also a metering, and this should be the same, that we are talking always about the same place.
Right. If you want, I can share your screen right now, if you want to go through.
It's okay with this, but it's okay with yours, what you wanted to say about the limits.
Oh yeah, absolutely. That's the main thing, is just go through some of that discussion point. But yeah, we can go through some of the results that you said. We could even revisit this. Okay, cool.
Yes.
So let's see.
It should.
Okay, so this is yep, I see it. I see a live rotating kiln. And we're doing pretty good on time.
Okay. Here, this is an example of a kiln which we have measured.
And the left is the discharge in, and the top right is the inlet in, right?
Yes. Can you see my cursor?
Yes. Yes, I see it on tire 3, or the discharge tire.
And this, yes. You see tire 3 is discharge and tire 1 is inlet. And it's written here outlet, and here up it's called inlet. And you see also here the gear. And with the cursor I can move around, I can zoom in. I mean, I can turn it, so we can see it from all places. And this software you can download. I mean, everybody can download it from our webpage, so it's there is no charge on it. I also recommend that whenever somebody wants to review some reports or measurement, that he installs the software, then he can review and look into the real data. I like it much better than a PDF report. PDF report is just for the archive.
Right.
But the real data is, and it's easy. Yeah? So you can open the file and you'll see. So you have the measurements here. So that's what you showed in your workshop. Yep. So that are real measured values. So that are the curves. That's a line chart, but you can also use look on it as a radar. So it becomes more, how you say, more understandable. It's more easy to see.
Right.
So we
can. And your typical zero is at the manhole, right?
Oh yes, for the rotation. That's another zero.
Yeah, yes. For the rotation.
Yes.
Yeah,
exactly.
Yeah. Your angle zero.
The angle zero, the rotation zero is usually on the manhole, but also for that, I mean, I recommend to have a line. It would be good if we have a line along the whole kiln. That would be the best. If we not have, then it would be good if we have right and left on each tire. We would have a marking which shows A, B, and C, like we use it for the ovality sensor. And then we are using the A mark for the rotation. The A would be the F. And that gives us then the zero. So each time when the kiln, the point A is exactly in the direction or in the line of the laser dot, from this kiln gel laser, we push the F9 button or the marker button. It's that one here. Set mark, it's F9. And then with that we say here we are on zero. And then when we have the different
on the marker, I actually like what you did new with it. I think it's last year or so you added the sound. You added a beep. Because I was doing some measures yesterday. And that was the plant was kind of loud, but that actually helps. I was like, oh, okay, it marks, because it's not so easy to look.
Yes, you're right. Sometimes maybe the fans around the kiln are too loud, so you cannot not hear the sound of the beep. But still, we will. The next in one of the future version, we will also get a bigger button that you don't need to look on the screen to hit the button. I mean, in the if you use a laptop which has a keyboard, it's the F9. It's the same. But if you only go with a tablet, which is nowadays more state of the art, is when you go with these industrial tablets, then you not have an F9 button. Then you have to hit the screen on the right place in the right moment, and for that we will add a bigger button for that. But back to the screen here. I mean, that's the kiln. So you see where we are, and here is the table. You can go make it smaller or bigger. Here is the table that were all the measured positions. You see position in meter. So here was measured every half a meter, here every meter, so in different places. Here when we, for example, when we select here meter 47, you see that here the cursor, the angular cursor is moving to that place, so I can see here. And when I go up with the arrow button, I can go navigate up or down. The cursor is jumping to the place where we are. Then we can put also the kiln into to the straight view, and then
that reminds me, you can integrate the tire wobble measures into this.
Oh yes, exactly. Yes, And this is, I think, related to the kiln shell, to the deformation. This is one of the very, let's say, the very great advantage when we can integrate the wobble of the tire into the same model. Because usually the tires, they are wobbling because of deformation in the kiln shell. And they are not just wobbling because they like to wobble. They are following the shape of the shell. And that's why we should have the opportunity to see how they are linked. Because if we want to correct a tire wobble, we would need to cut the kiln shell. And for that, we need to know where we have to cut it, and this can be found out easily here. So and that's why that's then the power of a 3D model. And then that's why it's much better than something just on paper, you know, a printout.
Right.
So that's why I like when we can have a look into it, and we can stop the kiln on any how we say, on any position. So go speed down, or I can go with the speed up, and I can turn it. You see. And it's much more visible how the gear is wobbling. Of course, the gear is very much amplified. It's exaggerated. It's very small values give here on the gear already big, you know, a big wobble.
Hey, I do have a comment on the wobble. So I took some wobble measures the other day, and I had a customer ask me if they could double check me with the dial indicator, and it came out very close, in inches, within 5-10 thousandths.
Oh yes. If you have the chance, yes,
great.
if you have, yes, thank you. Yeah, I mean, if you have the chance to measure it with a dial indicator, then it's okay. But the difficulty with the dial indicator is that the surface needs to be clean. And with the sensors, with inductive sensors, we can measure over any dirty surface. It doesn't matter.
Right.
So what you also have shown is the other one is the grid, huh? The grid.
Yeah,
so
the grid.
Yes, and with the grid we can see inside the center line. You see the blue line? That's not the kiln axis. That's the shell center. The blue. That's of each cross section of the kiln has a center point, center of gravity or center of geometry, and all these center points in a row gives then the blue line you see here.
Right, and the denser points are just denser measures.
Oh yes, you mean the denser line here?
Yeah, axially it's just closer, right? So there's more measures here than the rest of the unit.
Oh yeah. Here was measured. It was measured every half a meter. So that's why we have more. We have more lines. Yes. Here less. But that has no. It's not related to the kiln. It's just because here it's more deformed. So then the people who measured that, they took more readings. So they every half a meter instead of every meter.
So if you go back to the amplitude view, what are some conclusions and some interpretations on that deformation that you have?
Yes, I mean,
so it looks like the deformation is high.
Yeah, here. So it's around meter. It's about meter 13. If we go here to meter 13, then we see the values. Here, meter 13. You see now the grid is here. Make it a little bit slower again, but we don't get. So it is so.
And that's typically the hot spot or the hot end anyway.
Yeah, that's in the burning zone. Yes, exactly. So what I can show you is here. You see here the total runout is plus minus 30 millimeter. So it's more than 2-inch peak. And this is the round. It shows you the roundness deviation. It's the total runout. And the total runout is what we measure with the laser. So the variation when we think about the medium or average distance from the laser to the kiln shell is here changing by plus minus 30 millimeter. So in total 60. The shortest to the longest distance is 60 millimeter. So that's quite deformed in this area.
Right.
But this is only one part. I mean, the amplitude is not it's not the most important. Let's say it's important if we want to fix a new piece of shell to the old one. Yes, then it should be round.
Right.
But for the, let's say, for the refractory life, it's more important how smooth these deformations are. If we have a small deformation, but it's a very sharp step or abrupt step, then it's much worse than if we have, let's say, a nice egg shape. Then with a nice egg shape, we can still install refractory somehow in a good way. But if we have a sharp step inside, then it's more tricky, and that's why the first thing is for the consideration regarding refractory is more on the sharpness. And for that we have added the curvature view, and this is here. When we go for curvature, now you see what is here is heavily deformed, but still it's not that bad, because when we see in the radar chart, is here, you see that are somehow smooth curves. I mean, it's not nuts, but it's also not that bad, even if it's with high values. We are talking about plus minus 30 millimeter, but these deviations are not that sharp, and that's why it's not so critical. I mean, if somebody would say, would you recommend to replace this area of the kiln shell, I would say, yeah, first have a look into the brick life. If the brick life is bad, if the brick life is reduced by this deformation, yes, of course, I would say replace this area. If we not have issues, and this is really possible, that we not have much issues, because anyway we replace this refractory maybe every year, so it's normal lifetime, so we can reach it. So it depends. It depends. But sometimes when we get asked, hey, we have a frequent refractory problem, and then we don't know if it's from process, if it's from installation, if it's brick quality, or if it's the kiln shell. And to find out if it's the kiln shell, then it's quite easy with the laser. You place it and you immediately can tell if it's round or not. So
I see. So it's really good measure, but you want to qualify with some additional questions.
Yes, of course. I mean, if somebody says, hey, in this area we have trouble with refractory, could it be from mechanical? I mean, from roundness? Then I would say yes. This here, yes. If they say, yeah, but we are suffering more in this area, then for sure not. It cannot be the reason. Cannot be something mechanical in this area.
Right.
I mean, then when we are under the tire, then it's a story from ovality, and ovality we would not see here. But you see here, this is another type of view, is the topography. It's like a landscape. So if we open the kiln shell, so if we look from here, exactly from the front at this meter, it shows exactly the same as when we go to the line chart. It's that. In the line chart we have it easier. I mean, here we have nice millimeter view, but the line chart and that one is the same. It's just a radar, and this is line, and then we have the topography, and you can display all at the same.
Right. For you guys looking at the topographical view, because I get asked this, that is not a temperature color. The blue is the low point, the red is the high point, and the green is about a neutral point. So just remember that. And there's a graph on the right that tells you more details for the
Yes.
amplitude view of it.
Yes, exactly. We can see it in the topographic view. There is a how to say, there is something which shows that. I have too many. So here
right.
Too many windows. But it's just to show you if you want to evaluate. You can have the different graphs open. You can even make full screen. You can bring them back or have a full screen here. With that, then you can read it better. Maybe what we also can see is the center of the geometry and the center of rotation. And yes, and what you said with the red and blue, yes, it's not related to temperature. Blue is going towards in and red is sticking out. And when it's green, there is almost no deformation. So,
right. Well, cool. Anything else you want to show on the software?
Yeah.
I mean, this is a new setup ultimately compared to even a couple years ago.
Oh yeah. I mean, we are continuously working on the software. It's improving, and we add more features. And here you see also the grid. So the dark red is 30 millimeter out. The dark blue is 30 millimeter in. So that's the, yeah, I mean, everything is a question of amplification.
Right.
So you see, you can
make it look really bad, or you can make it look not so bad.
Yes, so that's why in the report we have standardized the range, that when we browse quickly through the report, the printed report, that we can compare easily without looking to the numbers. But in the software we have features that we really can zoom into it. And but this zoom will be reset when you close and open it again. You will have the standard view. Then it's more easy when you see different kilns in a short time. Then it's more easy to compare them. Otherwise, we get tricked by the amplification.
Right. Well, cool. Well, I appreciate the software discussion. I'm gonna go back to my screen. Okay.
Yes,
so
there is much more to do with the software because we can combine all the measurements, as we said.
Oh yeah.
The wobble of the tire, the wobble of the girth gear. Then we can make the same with the inclination. Then the kiln axis is one of the very important point. Then we can also visualize the axis. So all is in one roof in one file. It's one file.
Yeah, that's what I noticed is you've started to unify all the separate measures into one piece that you can see visually along with the data. I think that's really cool.
Yes, and it's also possible that when you measure with different people measure on the same kiln, that when you get a new set of data, another measurement, you can add it to the same, to your file, to your kiln model, you can add. If you have 1 month later, you ask somebody, hey, please measure me the run out of the girth gear. Then he can send it by email and you can drag and drop it into the kiln and then you have the gear run out as well. But for that, it's very important that we are using the same reference points. For the rotation. Yes. Otherwise, it will not match. And that's why I recommend put ABC around the tire, which may be welded or marked, that they are permanently visible, that next time in a year or two, but if somebody goes and measure that, they are talking about the same. And then we can really merge the things to one 3D model.
Right. Yeah. I mean, even when we go on job sites, if the customer has A, B, or C on there, we use that as our reference point. If they don't, then we'll go ahead and find the manhole and put A on the manhole and reference everything to the manhole. Then I think, like you said, it unifies all of it. Even if we go back, say, a year, 2 years, and do it again, it's still the same reference points.
Yes.
So, okay, cool. So awesome. So any additional comments you want to make on the limits? Because you showed the curvature view a little bit.
Yes. I mean, the let's say, the origin of this curvature view comes from that slide. And this slide is the relation, let's say, for a deformation, which we hopefully not have in the kiln or not many. So the relation between the area which is deformed, the length, and the height, the amplitude. Because when we have, you see it in the lower one, when we have a very smooth, I mean, this applies in the length and it also applies in the circumference. It's the same. When it's very smooth or when we have a nice egg shape, it's not as critical, not as seriously as when we have something, a sharp deformation, a dent, like on the upper one. If we have something, we call it here sharp or whatever word we use, but when it within a short distance, when we have a lot of changes, then it's much more difficult to install refractory.
Yeah.
Even so, the height is less. Even when the height is less.
So yeah, I say you say sharp. I would probably say steep.
Steep. Mm-hmm.
Yeah, and just international wording, right?
Yes.
Okay, so yeah, I mean, Thomas, that actually covers a lot of what I wanted to cover on the laser. Is I wanted to show the tool itself. I wanted to show everyone a little bit on how it looks when it's shooting or measuring, and then some of the data afterwards that you've shown and some of the interpretations. So that kind of wraps that set up. So what I want to do next is just kind of summarize what we've talked about. The ovality, I mean, we've talked about 4 different tools. We talked about the ovality sensor, how it's important for refractory life, how it ultimately measures the deflection of the shell in and out. The gear runout, how it's good to measure the runout as it's running, and compared to a traditional dial indicator set, you could do it while it's running. That's the key, along with capabilities of measuring crank and measuring tire wobble. Measuring wheel is pretty self-explanatory in the sense that it measures diameter, but the key is it can show taper, it can show concave, convex. Kiln shell laser, we just talked about, measures the deformation of the shell. Graphically shows a lot of the changes, how you talked about how important it is to look at the details and interpret off of it. And ultimately, you're taking almost all of this and trying to put it all into one system. So next things are, from IKD's standpoint, again, we're the exclusive distributor in North America for TomTom tools. We offer training for the TomTom tools, troubleshooting for the tools, repair work, especially things that we can do here in-house. It's a lot shorter distance to fly something in North America to us in Louisville, Kentucky. And if it's something that's more critical, that's harder to handle here, then we would work with Thomas and his team over in Switzerland. And if you need that tool now, we can even help you kind of get you guys going while we work on the repair, and we'll work out some details on it. And we, in our website, have all the TomTom tools displayed in www.industrialkiln.com/tools/TomTom tools. For Thomas, what I want to specify here is we haven't covered all the tools. This is just maybe half. There's the kiln axis alignment, the mechanical monitoring system, the rotary inclinometer, the creep monitor, the bearing temperature sensor. And I know Thomas well enough that he's always looking at what is another tool that can solve another problem. Any comments you want to make on this part, Thomas?
Yes, thank you. Yeah, that's what we are doing. Yes, we are looking, or let's say we get asked many times, yeah, do you have something available for this or that, and so on. So that's why we are trying to develop something if it's not already existing. So and yeah, so we come to more tools, so like this bearing temperature, where we have sometimes the issues that bearing temperature increase is, is a warning, but it's a very late warning, and that something is not good in the bearing. So we need to catch the temperature increase on an early stage, and for that we have developed a small sensor which can be easily installed in, I would say, almost all the bearings on cement kilns. Then with the kiln axis, if we have a situation, or we would like to measure the kiln axis ourselves, when it's not too complicated, then we can do it ourselves. So, but for a tricky situation and how you say to solve misalignment, maybe we still need the experts. So we should not replace the service of a surveyor, but it should make it possible that for a quick check to see that everything is fine, that we can do it ourselves. I mean, as cement, cement plants, they should be able to do it themselves. Later, when they have detected that there is a problem, bring the specialist, fix it. If it's not possible that they fix it themselves. So for that, I think it's and it's an easy way. Watch the video and you will see it. It goes quick.
Right.
And cool. The other one is the inclinometer. This is also a quick check if we have a problem with the slope of the rollers, if it's not matching to the slope of the kiln or the slope of the tile.
Right.
So that's the thing. And then we are working in fixed installation. As I said last time, I mean, everybody talks about the Industry 4.0. So we want to have, everything under control. We want to know everything has to be equipped with sensors. We want to have, let's say, artificial intelligence on top of all the sensor data. But for that, we need reliable data. So we need a reliable creep. The creep and should be linked to the kiln shell temperature. So with the creep, that's why we developed a new version of the creep monitor. Then also crank has to be measured, because the crank is the main problem for broken roller shafts and broken tires. So that's why some years ago we developed the MKM system. Now we are on a new setup where we have the different function of this mechanical kiln monitoring system available as a simple single unit, easy to install, and this is then a source for reliable data for this kind of data analytics. You know, that we have the reliable crank values, the reliable creep, also temperature on the shafts, and also the kiln position, the axial travel. So that's
right. Well, cool. I mean, there's a lot of stuff, and I know you and I work together on going, okay, what can we do this? Can we do that? And we run into problems all the time where if we could measure, that'd be great. But I mean, it's always exciting to see what's new, what's being developed. So we always appreciate the working relationship. So overall, we finished our TomTom session. So for everyone on each of the sessions, it's actually recorded. We got session 1, 2, 3, and 4. This is the end of it. We appreciate you guys, especially the guys that made it through all 4. listening to us and getting feedback and asking questions. Again, if you guys got any other questions, feel free to contact us, industrialkiln.com, 877-316-6140, contact industrialkiln.com. Again, with these times, we're essential, we're open, we're ready. With that, we appreciate it. Thank you, guys. Thomas, any last words?
No, bye. Watch the video and the webpage, and there is a lot of more information. But thank you very much for having the opportunity to do these webinars with you. It was a pleasure. Thank you.
Absolutely. It is a lot of fun. Well, without further ado, thank you, guys. Stay safe, stay healthy. Thank you. Bye-bye.
Thank you, sir.
Thank you.
Thank you.
Thank you.
Bye. Bye.
Bye-bye. Thank you.